So to finish this unit, we were, the last lesson we finished off by talking about outliers in a set of data that we can make a least squares regression line for and do some analysis of it. Okay. There are different types of outliers, but we give them different names and we call them influential points. So they're points on a scatter plot or in a set of values that somehow can influence how the least squares regression line looks, which means it could affect the y-intercept of the line. It could affect the slope of the line. It could affect the correlation of the relationship, which means it affects the correlation R squared. It could affect the standard deviation. Okay. One thing, it is possible by hand to find the equations of these lines. Remember, to find the equation of a line, which you learned way back in grade 10, you need a point and you need the slope. Okay? Well, there is a point that exists on every least squares regression line we do. So this is the example we did early on in the unit about the grocery, about the income in a certain zip code and the number of organic items available at a grocery store at HEB in that zip code or in that area. Okay. Can you think of a point that would always be on the line? It's kind of giving you a little bit of a hint here in the graph. There's one point that's going to be on every regression line you do, and we can use that point to find its equation. That point is the mean of the x values, comma, the mean of the y values. So if you take the average of all the x values, take the average of all the y values, that point, when you put them together, will always be on the line. And then you can actually use standard deviation to find the slope, but we're not going to talk about that. Okay? We're actually going to use our graphing calculator to help us find least square regression line equations. So for example, in this one here, all the incomes that were listed in the different zip codes, the average was about 70,000. So a little bit less than 70,000. And at a little bit less than 70,000 on the least squares regression line, we get about 52 items. So this point here is the point 69,198, comma 52. It will be right on that line. Okay. So points on the scatter plot that have a certain influence on the line. First of all, we're going to talk about leverage points. Leverage points, okay, tell us how close data values are to the median of the, or mean of the x's. Okay. So if we have this here, like if we go low leverage points are close to this. Okay, they're close to the x value, not necessarily the y value. They're close to the x value. So what we can do is basically take a box like this around the x median, x mean, and take those points out. If we take those points out, Does it look like it has a huge effect on the line? Does it look like it changed the slope of the line or the y-intercept? No, not really. Okay, yep. There is, but we're not going to worry about it. Yeah. Okay, we're just basically learning the influential points, what they mean. So, no. I mean, if you look, the y-intercept here, I don't know, looks like it's around 15 or something like that. Looks like it maybe went up slightly, but not very much. Slope here doesn't look very different. Okay. So, no. The y-intercept and slope didn't change much. However, if we go further away from the x mean, those points that are further away from the x mean become high leverage points. So here, way out here, would be high leverage points because they're quite a distance from the x mean. So if we remove those, and compare the least squares regression line to when they were in there, there is a difference. Okay? The slope did change, and so did the y-intercept. So we would say high leverage points are far from the x mean. So yes, slope and y-intercept did change. The point I'm trying to make here is that if we're points close to the x mean, if we take them out, they're not going to have an impact on the least squares regression line. The further we are away from the x mean, either direction, okay, they're going to have more of an impact on what the line looks like. And by what the line looks like, I mean slope, y-intercept. So those are leverage points. So we talked about outliers and leverage points. Those are types of influential points. And what's an influential point? It's a point that if we take it out, it's going to affect all the characteristics of the least squares regression line we've talked about in this unit. It's going to impact the slope, the y-intercept, the correlation R, the coefficient of determination, that's R squared. So let me just put these in here. The slope, which we call B, the y-intercept, which we call A, the correlation, which we called R, the coefficient of determination, which we called R squared, the standard deviation of the residuals, which we called S. Some, if not all of them, will be impacted if these influential points are removed. So here's a few examples. So here again, we have a high leverage point. It's quite a horizontal distance away from the mean. Okay? And we saw that it changes the slope and y-intercept. So if we took this one out, it's going to take this line and tilt it like this. So it's going to change the slope, and it'll probably increase the y-intercept and decrease the slope. Because if we took it out, we'd probably be looking at something more that looks like this, maybe a little bit higher. Outliers we talked about. Okay, this is back from the previous lesson. What do outliers do? Well, we talked about that. It can change the correlation, or which means if it changes the correlation, it's going to change R squared, or the coefficient of correlation. That's the square. And it also changes the standard deviation of the residuals. Which is S. We saw that last class. And usually if one changes, if R squared changes, S changes in the other direction, right? So if R squared increases, that means that S is going to decrease. If S increases, that means that R squared is going to decrease. Here's an example of a point that would really be bold. Not only is it an outlier far away from the line, but it is also quite a horizontal distance away from X mean, from X bar. Okay? So what will that do? Well, it's just sort of common sense. If it's bold, that means that it changes everything. That's really all you need to know about influential points. We're not going to go into any calculations like we did in the first unit when we actually calculated whether something was an outlier or not. Okay? You just have to be familiar with sort of what happens to these characteristics when influential points are removed. Okay, to finish up, now that we've talked about everything, how do you use a graphing calculator to get the regression line? Okay. Well, you're going to have to enter some data. And remember, when we were calculating in the first unit, mean and median and Q1 and Q3 and standard deviation, we entered the list of numbers, right? Well, this one, it's two variables, so we got to enter two lists of numbers. So we're going to take this example. Following data gives the weight in pounds and the cost in dollars of a sample of 11 stand mixers. Okay. So a weight of 23 pounds costs 180 bucks. A weight of 26 pounds here costs 370 bucks. We're going to see what kind of relationship this is. So, do you remember how to get to entering a list? Stat. And then it'll say edit highlighted, and you should have your list columns. If you need to clear your list columns, scroll up to L1, hit clear and enter, and it will clear all the data for you. So under L1, we're going to put the X values. So 23, 28, 19, 17, 25, 26, enter. Don't forget to hit enter after that first one. Now, right arrow key takes you over to column L2. So 180, enter, and then etc. 250, 300, 150, 300, 370. And don't forget to get to enter after that 370. So you've got your data entered. So now we want to go to the function that's going to calculate everything for us. So to get out of this list, just go second mode. Okay. Now, before we do this, hit mode again. And if you scroll down all the properties there, you should see something that says Stat Diagnostics and Stat Wizards. Both of those should be on. Just make sure both those will, and then you don't have to worry about it again. Okay, but just make sure both of those are on. And then second mode to get out of that screen. Okay. So now what we're going to do is we're going to go back to stat. And instead of edit, we're going to go over to calc. And we're going to do linear regression, but not number 4. Remember the form that the equation took? A plus bx. So you got to scroll down till you get to number 8, where it says linear regression A plus bx. Hit enter. Your X list should be L1. Your Y list should be L2. Don't worry about frequency list or store. So just go down to calculate. And it gives you all the values you need. So it tells you A, which is the y-intercept. It tells you B, which is the slope. It tells you the correlation, 0.49. It tells you R squared, which is 0.24. All right, so here's how we do it. Well, first of all, I'm going to just put over to the side here, R equals, and you can go 2 decimal places, 3 decimal places, 4 decimal places, really doesn't matter. Okay, I usually do 2 or 3. So R is going to be 0.492, and R squared is going to be 0.242. Remember A which represents our y-intercept. I'm just going to say 38.556. D is going to be 9.556. And now you got to write your equation from this. Remember, it's in the form predicted y, or y hat, equals a plus bx. So therefore, our equation is going to be y hat equals 38.556 plus 9.556x. But remember, we're always answering in context. So you need to, using words, define your variables. So y hat is going to be the predicted price. Remember, whenever it's y hat, when describing it, you've got to use the word predicted. Predicted price. And x represents the weight. So this is a completed answer. You don't have to write like this stuff here. You can go straight to the equation, but you've got to write what the variables represent. And then, of course, write r and r squared. Lastly, you may be given data in the form of a computer printout. for a regression table. You have to be able to read these. In other words, you have to be able to get all the characteristics that we talked about of least squares regression line, the equation, S, R squared, etc. So here, when you look at this data, you're going to ignore some stuff. Okay? So we need to identify the equation of the least squares regression line. And then S, R squared, etc. Okay? Well, to get the line, the equation of the line, that constant and the value right beside it will represent the y-intercept. And remember, in stats, we call it A. O, the income, that represents the slope. Which we call B. X down here, yeah, it represents the last standard deviation of the residuals. R squared, remember, R squared, we didn't express as a, we expressed it as a decimal. So R squared would be 0.617 as a decimal. There's only one piece of information that I'm missing, R. You can't, R is not given on the table, but how would you find it? Take the square root of this. So R is going to be the square root of 0.617. However, when we solve for R, when we solve a quadratic equation by square rooting, we always take the plus or minus square root. That's important because, remember, R can be a negative value, can't it? Or R could be positive. When is R positive? When the slope goes up, when it's a positive slope. When is R negative? When the slope goes down, when it's a negative slope. Is the slope positive or negative? It's positive, which means that our answer is going to be the positive square root of 0.617, which is going to be positive root 785. That's a pretty strong relationship. Whatever this is. Notice, oh, sorry, I need to write. So then we would say y hat equals negative 14.7, the y-intercept is negative, plus 0.001x. However, I can't define my variables here because I don't know what they are. So that's the best I can do. But be careful if you're asked to calculate R from R squared. Watch out for that. Okay. So let's just look at this grocery example one more time to finish up. Where we can actually use prediction as potential discrimination. Because remember the two variables we were talking about, average income in a certain zip code or area, and the number of organic items available at that grocery store in the area. And we saw that it was a positive, linear, quite strong, moderately strong relationship with really doesn't appear to be any outliers. I remember the 4 components that you have to describe. So this grocery store chain wants to open 2 new locations in San Antonio, one in the lower income zip code, one in the higher. Based on our least squares regression line, how many more organic items are predicted to be offered at the location in the higher income neighborhood? Well, how would we do that? Just use the least squares regression line, which, oh, actually, that was on the previous page. I didn't realize that. Okay, then. This is the HEB example. Let's put that in there. So we can actually define our variables by half of these predicted organic items. And X would be income. If we can actually, yeah, that's the HEB example. Okay, well, to do this question, it's pretty straightforward. Just use the equation, which is negative 14.7 plus 0.001x. Well, you're given the mean income of the low income area. So we want to find the predicted number of organic items they're going to offer. So for the low, y hat is going to be negative 14.7 plus 0.001 times the mean income in that area. And then we calculate that. I know it's decimal 20.3 items or 20 items. It's fine too. For the high income area, the predicted number of organic items is going to be negative 14.7 plus 0.001 times the mean income in that area, which is 115,000. And that's going to give us 100.3 items. So we can see, obviously, the store that's in the high income area is going to offer a lot more organic items, 80 more. 80 more organic items. Offered. In the high incomes. Quite a discrimination. Okay,